Okay, good morning, everyone. Um, all five of you. Um, so you had your first experience with integrals. How did it go? So any questions on 5.1? That's good to hear. One comment here. That's good. Anyone else?
I think it was relatively easy.
Okay. I think you're right, but okay, good. All right. Well, as you can tell, the topic today is we're going to just start. I think I had told you that integrals actually eventually will open up into finding the areas under curves. And you can tell that already with the title of this section, area. And we're going to be spending a lot of time today with sigma notation. I'm not sure how familiar you are with that, depending on your background, maybe with statistics. But it uses this, it basically right here, it's that Greek capital S. And the name of Greek capital S is sigma. And sigma, because it begins with an S, basically it stands for sum. Sum. So it's a sum notation. As you can see, it's index of sum. So what this symbol means here is we want you to add up all the A sub i's from 1 to n. That's this note, so there's a little index here. That's the subscript I, and that is basically controlled by the beginning and the end, which are on the bottom and the top of the notation. So it says add up all the A's from 1 to n. And so you can see, I know n is not very specific, but nevertheless, here's how that comes out. Add A1 to A2 to A3, all the way up to AN. Often, the I, J, and K are often used as index letters. It's not real important, but when you see, I don't know, it's just a common practice. Okay, so here are some examples of sigma notation. So in part A, it says add up all the indexes from 1 through 6. All the i's. I equals 1, I equals 2, I equals 3, and just keep going up by 1 until you reach 6. Okay, so this notation can be useful. Otherwise, we could just write out 1 plus 2 plus 3 plus 4 plus 5 plus 6. Notice there's more than one way to write that particular sum as you look at part B. This time, the index goes from 0 to 5, and we are to add up all of the I plus 1s. So when I is 0, 0 plus 1 is 1. And when I is 1, 0 plus 2 is 2. And you wind up, so you can see already that there's more than one way. Sometimes there's more than one way to express a sum. Just look at the other examples. Basically, the index gets, like part C. For J, starting at 3 and going to 7, we want you to add up all the squares. So starting with 3, 3 squared, plus 4 squared, plus 5 squared, plus 6 squared, plus 7 squared. Okay. A little more general, down toward E. 1 over n times k squared plus 1. And the n is what? The ending number. And we don't know what that is. But we know k starts at 1 and goes up until it gets to n. So when it says find the sum of 1 over n times the quantity k squared plus 1, first thing we're going to do is replace k with a 1. That's what they did right here. And then next term, replace k with a 2. And keep going until k is an n. Anyway, I'm trying to get you used to the notation here. And of course, function notations are sometimes used. So here we want to go from 1 to n. And we want to take f of x sub 1, 2, 3, 4, whatever different x it is, goes from 1 to n, and take that times delta x. All right, so there's some examples, and it's going to take maybe a little while for you to adjust. I don't know, depending on your background. So now I'm going to tell you a little bit of a story here. Carl Gauss, famous mathematician. Supposedly, the story goes like this. He was in grade school, and his teacher had a headache. And the teacher said, he just gives them an assignment to keep them busy. He says, I want you to add up the numbers 1 all the way to 100. And within 2 minutes, Carl was raising his hand. Ooh, I got it. And here's what he did. He basically, in his head, said, all right, well, let's list the numbers 1 through 100. That's what you see on this top line here. 1 plus 2 plus 3, all the way up to 100. And then I'm going to make another list, only this time I'm going to count backwards. 100, 99, 98, and so forth, all the way down to 1. And he realized that when you added up each of these columns, you always got 101. 100 plus 1. 2 plus 99, 3. So he said, all I got to do is take 101 times how many of them there are, 100. Of course, I'm going to have 2 lists, so I got to divide it by 2. And that is the correct answer, 5,050. So here's how that's expressed at the bottom here, using summation notation. From 1 to 100, add up all the numbers, add up all the i's, and it turns out that his shortcut is correct. And in fact, here is one of the properties we're going to learn today. When you add up numbers from 1 to n, it's equal to n times the quantity n plus 1 over 2. N being what? 100? From 1 to 100. 100 times 101 divided by... Anyway, this turns out to be a very important formula, one that you're going to probably have to learn. You're going to have to know that. Just kind of an interesting little history. And here are all the famous, I guess you could call them the summation. Yeah, like it says, the summation formulas. I mean, here's the one we just did right over here. That's the one we just did. And Carl Gauss came up with that. Yes, I know, he was in grade school. Pretty cool, though. All right, now look at number 1. So this one says add up a constant how many times? 1 through n. So in other words, it just says add up c n times. Oh, isn't that just cn? That's another fancy way of saying multiplication. So very simple, and yet that's important to know. So if you're asked to add up a constant n times, it's just multiplication, cn. Now these two are not natural at all. If you want to add up squares from 1 to n, that is 1 squared plus 2 squared plus 3 squared plus 4 squared, etc., up to whatever n might be. Here is a formula for doing it. I mean, for example, if I told you to do that sum, so here, let me write it out. So what if I asked you on a quiz to do this? If I said do this sum, so if I asked you to do the sum of I squared from 1 to 100, you realize what that means. You'd have to take 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to 100 squared. We're talking a major long calculation, okay? Well, if we use the formula, what do we have to do? We have to take, the shortcut says, take n, which is 100, multiply that by 101, n plus 1, then multiply that by 2n plus 1. Well, 2 times 100 is 200, so 201, and divide by 6. That'll give you the answer. A major shortcut, okay? And then there's also, in number 4, there's also a shortcut for adding up cubes. N squared times the quantity n plus 1 squared divided by 4. Okay, so I mean we're not going to give you a lot of these at this time. We're just giving you these 4, but they're pretty important. Okay, so now let's take a look at example 2, evaluating a sum. So we've got this sum formula right here. From 1 to n, add up I plus 1 over n squared. And they want you to do it for these different numbers. We'd like to do it for n equals 10. Separately, do it for n equals 100, and all 4 of those. Okay. So here's a case where some algebra comes in really handy and some properties. Instead of actually whacking away and doing it the long way, we're going to pull out the n. N is a constant, of course. For I equals 1 to n, that has to be designated. That's a constant. So we can pull out the 1 over n squared, just like we could do it with derivatives. You can pull it out. So it's out of the sum. And then what's left is I plus 1. All right. Now, this step says, hey, you can do the sum in parts. You can do the sum of I plus the sum of 1. So you can break this into separate parts. Well, what's the sum of I from 1 to n? Well, we just had that a few seconds ago. That's the Gauss. This is the Gauss formula right here. Take n times n plus 1 and divide by 2. Okay. And what happens when you add up 1 n times? It's just 1 times n, or n. Okay. So before we do any sum or anything, can we simplify this now? Yeah, let's get a common denominator. Let's call this 2n, this could be right here. This n over 1 could be 2n over 2. And then we have a common denominator 2, and we brought it into this form. So, and then let's multiply by 1 over n squared. Well, what's n squared over n? N. And then, so you can simplify that down to this. Okay, so now that we know we have this nice shortcut, now let's go ahead and do the problem for what they said, 10, 100, 1,000. Okay, so all we got to do is take n plus 3 over 2n. Well, what is that? For 10, it's 13 on the top and 20 on the bottom. And if we just do that, 13 divided by 20, you can see we get 0.6500. Okay, let's do it for 100. So we now have 103 on the top divided by 200. You can see that's the 0.515 here, and so forth. Okay? Here, let's just do one more. Let's do the 10,000. So that would be 10,003 divided by 20,000. And you see that last number there, 0.50. So, okay. So here's what I'm trying to show you is here in this problem, before you whack away and do all this massive repetitive sum addition, you can sometimes do algebraic simplification ahead of time. Then this is outstanding because look at this. This could be a mess, and all we have to do is do this simple formula: n plus 3 over 2 over 2n. Also, do you notice something about where these numbers are headed? As n gets quite a bit bigger, what's happening to our sum? Seems to be getting closer and closer to what? 0.5? Yeah, so now what I'm going to do is I'm going to recall here. Let's do this is from what? Our previous chapter. So what's the limit as x approaches infinity of n of, well, excuse me, I changed variables, of x plus 3 to 2x. Notice the numerator and denominator both have a power of 1. The ratio of the leading coefficients. Oh yeah, 1/2, 0.5. All right. So we have a nice connection with something we've done previously here. Okay. Now, we're going to talk a little bit about area. So here we have an upside down parabola. Its equation, you can see in the blue, is x squared plus 5. Okay? And what we've done is we've drawn in some rectangles that fit underneath the curve. And as you can see, we don't have this exactly. We're not going to have the same area because we've got this pink area here that is not included. But if we added up the area of these gray bars, it would start getting pretty close to the area underneath the parabola. Now, I'm not going to have you do this right now, but here's the idea. All right, what's the height and width of each rectangle? Well, you notice how each bar is a width of 2/5. So from 0 to 2/5 is 2/5. From 2/5 to 4/5 is 2/5. So each bar is 2/5 wide. That's this part right here, wide. And each height is f of, and it's 2i over 5, where I goes from 1 to 5. So in other words, when I is 1, it's 2/5. And they're using, you see how we're using the right side of the rectangle? It's at 2/5. When I is 2, this would be 4/5. 2 times 2 over 5. Oh yeah, then we're over here. When I is 3, then we're over here. So this is a way of expressing the sum of the area of each of those rectangles. Okay, now what is f of anything? Well, we got to use the function. So you notice here, they took the x value, whatever it is, they squared it, and then they put a minus sign on it, and they added 5, which is exactly what this function tells them to do. Anyway, I'm not going to go through the details here because it's kind of excruciating, but it comes up with 6.48. And what do you think is going to be true of that answer compared to the parabola? It should be a little bit short, right? Because of that pink area we're not covering. So if you add up, right now, if you added up all the rectangle areas, you would not get the area. You'd be close. Okay, so another option we're going to look at toward the bottom of the page is, how about if we take the same width, 2/5, but this time we're going to take the left edge of the rectangle. So in other words, now we're going to take, you see, we're going to be over. We're going to be too high. The rectangles have some waste, as in the powder blue area. And this time, if you added up all the rectangles, you get 8.08. That's too high. So let's just go back. Too low, 0.648. Too high, 8.08. And the real answer is somewhere in between. See, what we're trying to do eventually is, how can we find the area of this, under this curve, this parabola? Well, how about if we made more rectangles? And so we're getting to the point now where if we take more rectangles, so here's our formula. Here's the height. Here's the width, delta x just being the width of the bar. And if we take the height times the width and add them all up, we've got those areas of those rectangles. But now look at this. How about if we take the limit as n approaches infinity? In other words, how about if we made an infinite number of boxes? And then, of course, we're getting really close. And if we take the limit, of course. Now, by the way, you can see by these rectangles, another option is, instead of taking the left edge as being the height, here they took, you see, the middle of the rectangle. So there's that option too. So here we go. What we're saying is, when you change the width of the rectangle down to nothing, you take the limit as that delta x approaches 0, guess what you get? The integral. The integral is the perfect solution. Now, you haven't seen this quite like this before, because you notice there's two things being added here. That a and that b. That makes it a definite integral. I covered up the a, but when you put an a on the bottom and a b, that's saying starting at the vertical line a and going to the vertical line b, if you take the integral, you will have the exact area under the curve. So what we've done is we've taken a series of rectangles and we've increased the number of rectangles. Do you see how we're getting closer and closer to the curve? And in fact, I mean, it's really getting close now. And in fact, you get the idea if we take the limit as there's an infinite number of those. El perfecto. We've got the area under any curve. So once again, I guess I would say the champion is the limit. Because of a limit, we can do it. We can do it exactly. Okay, so that's kind of where we're headed in this chapter, and it's another miracle of calculus. But let's get practice here on sums. Okay. So here, I believe this is from your assignment. It says, find the sum, use your summation capabilities of a graphing utility to verify your result. Well, we're going to use Desmos, and I'll show you how to do that. But so let's take a few of these. Let's take number 1. So we've got I equals 1 up to 6. And we're supposed to add. So what does that mean? It means add 3 times 1 plus 2 to 3 times 2 plus 2 to 3 times 3 plus 2 to 3 times, whoop, put that 3 in the wrong spot, to 3 times 4 plus 2 to 3 times 5 plus 2 to 3 times 6 plus 2. Okay, so here we have a 5, 8, 11. You're seeing a pattern here. 14. Each time it's going up by 3, right? 17. And 20. Now add those all up. And you'll get 75. Answer, 75. So I need you to get into this notation so you can tell exactly what is happening. The same expression exactly. The I is being replaced by 1, 2, 3, all the way up to the end of the index 6. Okay, so now I'm going to show you how to do that in Desmos. In Desmos, I'll tell you, Desmos never ceases to amaze me. All you have to do, if you want sigma, is type in the word sum. S-U-M. And right away, you see it changes to sigma notation. Okay? Now it's N instead of I, so we got to adjust for that. So we want to go from what? From 1, and then click up there, from 1 to 6. And then 3n plus 2. And you see Desmos has provided the answer for us there, 75. So it checks. Okay, so they want you to check these. So after you've done that, but I want you to do it the manual way so you really get to know what's going on. All right, let's go back. How about let's take a look at number 4 next. I'm going to take my keyboard off so I can get at the bottom of the screen here a little bit better. All right, so number 4. We've got the summation. J is the index holder this time. J from 4 to 6. 3 over J. All right, so what does that mean? It means first we're going to have 3/4 because J starts off at 4. And we're going to add that to 3 over 5. And we're going to add that to 3 over 6. Now all we got to do is add those. Uh-oh. We got to get, this is a fraction problem, and we need a common denominator. What's the lowest common denominator for 4, 5, and 6? I think we're going to have to go with 60. So 3/4 of 4, that would be times 15. So we have 45/60 plus 5 times 12. So we got to take times 12. And then times 10. And altogether, what do we have? 111 divided by 60. Let's just quick divide that out and see what the decimal is. 111 divided by 60 1.85. Okay, let's do it on decimals. So, need the keyboard now. Sum, and we have from 4 to 6. And this time we want to do what? And in our case, it's 3 over j, but in this case, it's 3 over n. Yep, 1.85. Okay, so the one disadvantage is, you know, you get the decimal answer. You don't really get to see what's going on with the fractions. But so anyway, I would like you to get into Desmos and do some checking here just to make sure and get used to some of this new notation. All right. Anybody have any questions on this? So now the next section says, let's see if you can write sigma notation. Okay, so what we have is no sigma here. They're just giving you some patterns. So like take a look at number 8. You can see what's the same in every one of those fractions. They all have a 9 on the top, and on the bottom they all have 1 plus something. What's the one thing that's changing? The second number, right? So we should be able to, so to write that with sigma notation, we're going to be changing this number, and we're going to start at 1, and we're going to go to 14. All right, and then what do we have? 9, 1 plus, and then I. So do you see how, sorry for the sloppy sigma notation there, but do you see how we can grab onto the pattern? Let's take a look at number 10. Okay, what's the same and what's being repeated? Well, in all the cases, we have a bracket, and we have 1 minus. All right, and then what's changing is the numerator of that fraction over 4. So I over 4 squared. Yeah, and that's it. And what is I starting at? I starts at 1, and it goes up to, and you look over here at the end, it goes up to 4. I guess I didn't need the brackets, but how about number 11? What's the same and what's changing? Well, we got 2 over n cubed. Yeah, this one's a little harder to see. What's the difference between 2 over n cubed and 2n over n cubed? Well, I mean, you could think of this being an n2 if n was 1, right? Over here. That's an n2 if n is 1. So now that's a little bit harder to see, but that's a clue. Okay? So we've got this. Really, we've got 2n. I should say I, excuse me. I over n cubed minus 2 over n, and then all of that is multiplied by 2 over n. And I starts at 1. That's n equals 1 right there in the beginning. And it goes up to, well, in this case, it's indefinite. It just goes to n. So I don't know if you're starting to, so you got to look for what repeats But in this case, you had to look real closely to see what's happening, because there was no n over there, or was there? Oh yeah, n equals 1. And so it's a little bit harder to spot in a problem of that type. Well, okay. Should be, give all of you an apple here for breakfast. The assignment, we'll leave it as it is there. 1 through 11 odds, and then added to that we have 15, 17, 37, 39, 47. So you're going to have to adjust to this new notation, become more familiar. Also, start learning. You should, let me get back to my, you want to start learning these guys, these 4, okay? You want to start getting to the point where you recognize them, because and you're going to see, you're going to make use of those on the assignment too. So whenever you've got one of those, you can get in there and you can make use of that. It's a huge advantage. So any questions? Clarifications needed? I'll go back to the assignment, since some of you, I may have gone by too quickly. 5-2. Well, thank you. I hope you have a great day. I will see you tomorrow morning.